Thank you. I see we're a lot like Italian queuing up here. It's exciting to be here. So many people around. It's really good to be here in Paris. Second time for PyData Paris, the first time in a long time. So it's really exciting, and we thought it was really fitting to come up with a paper and a talk about time series forecasting. My name is Luca. I'm a machine learning engineer in Extreme. Gabriele is an AI scientist there. We're really fans of forecasting. We do a lot of forecasting in Extreme, and we never used a foundation like time series transformer-based model in forecasting for our tasks. I wonder how many of you do forecasting here in the room? Well, a bunch of people. How many of you put transformer-based forecasting model into production? Yeah, right. Just for the records, nobody raised their hand. So one, okay, maybe we can talk about that. It looks promising. I think you can double check and fact check what we're saying. And basically, this is the point, right? A lot of people do forecasting. We've always tried doing a bit of deep learning with that. We've always followed the releases. We've always followed like the new trends and saw amazing results from incredibly clever and smart people that work on those models, which push out incredible benchmarks. And we respect those benchmarks. It's not like dissing or shading anybody. But when we try those on our private use cases, it's everything maybe crumbles or doesn't live up to the name, right? And so when we found out about those new papers coming out about zero-shot time series foundational model, our interest was piqued, and we said, okay, we need to look into this. So this is the result of a bit of an exploration that we did throughout the summer, Gabriele and I, and we didn't put any of that into production, just to be clear, but we thought that there might be something to it that we might want to use somehow down the line, because it looks like it might be a bit of a shift. It might be a new tool under our belt. So today we're going to discuss about what time series foundational models are, what's the definition, how they differ from a transformer-based model, why do they matter, how people build and evaluate them, and most of all, what we should pay attention to when we look at those benchmarks and when we want to try to gauge those models in our real-life use cases and eventually potentially in production. So without further ado, let's move on to the first point. Why should we bother doing transformers in production? Aside from the guy out there who did this, one of the reasons that we don't see them anywhere, I think is very well summarized by one point by Tim Januszkowski, who was the head of pricing in Zalando, who worked on the DPR paper and is now working at Databricks in Berlin, but he put out like a really valid point, right? So time series forecasting models, transformer-based models have been in production in places like Zalando since 2019, in places like Amazon, and he believes that that's because it's a function of data. So whenever we see those models in action, is that because the companies have plenty of data that they can use to train those models on. And his research group in Zalando published a preprint paper, I think it was this year, or maybe the end of the last year, where they published this paper and they were showcasing that some kind of scaling laws were kicking in. So when you have, I don't know, up to 500,000 time series that you can use to train a global transformer-based model on, you get decent performance. And this is where the reality checks comes in. This is not something for the reasonable scale company, I would dare say. We do not have 500,000 time series for the product that we sell that we can use to train a global model on. And for the reasonable scale company, we do not have such data. And maybe perhaps this is why we never use those things in production, even like powerful models such as DPR and its models. But it's exactly in a place like Amazon that researchers got an intuition, is that we can take even more data than the one they use to train their DPR-based models and try to do something akin to what we are seeing with LLMs. And so if you take the same recipe of a transformer-based model and you pick all the data that you can get your hands on, anything, right, no matter the domain, no matter the frequency, no matter the length, no matter the skewness of the data and how sparse it is, then you can use it to train a model from scratch. And you can hope that such a model picks up all the general patterns and then it learns the language, the structure of time series, which is incredibly not ingenious like in American sense, like really clever if you think about it. And it's been really amazing to witness such a thing and like throughout the past year, like so many models, foundational models have been released. But the intuition is really simple in an elegant way, like in a really, say, not like to diminish them, okay? But if you think about it, like if you can train a singular model on any kind of time series data that you can get your hands on, then you might find out that this model picks up the trends to forecast a city that is sparse, that is irregular, that knows the trends, the seasonality patterns, no matter the granularity. Which is a really big deal if you think about it. And what's the promise though? What's in for this, right? Because you need to have a lot of resources. Like the people from Kronos, we're going to see that. They've been trained their models on 800 GPUs by NVIDIA. So it's not cheap, right? And they give it away. And we can use it, but what's in for us, right? And I think that what we can find is that those models are zero-shot forecasters. So just as much as we can ask our GPTs to, hey, here is some data, extract the features, or find if this has positive or negative feedback. Just to be saying this is like, just to be clear, if you were at yesterday's presentation, this might not be enough or does not be enough reliable, but also enough fast for you to put in production. The thing about these models is that they are zero-shot forecasters. So you give them a new series, you don't need to train them, and they can give you immediately output predictions for that. Predictions, and also prediction intervals. So with one singular model, and then you see here there's the lure and the promise that these models want to sell you is that you can generate zero-shot predictions from a known time series that then weren't seen in the training data. And you can also generate prediction intervals for those, which is, I would say, something reliable. And if you think about it, is the real advantage is boils down in the end and comes back to the data thing. Because when you have such a model, you can, even if you just have a bunch of data points, you can use those to forecast. Whereas if you were a data scientist that receives a new task from the company, you would ideally have to wait to have enough data until you can train a new local model from scratch. Or if you have just enough data, you might want to train a gradient boosted model on all of those data sets that you have in hopes to train a global model that will have a decent performance on new data. When I say performance and decent performance, I will also mean compared to a reasonable baseline, because baselines like rolling average can bring you like really far away when you're in a rush. But you see here, the thing is that when you have such models, you might not want to have a lots of data, and just the tiny bit of data that you get started with might just be enough to put something into production with a decent performance. And the more data that you get, that might not be used to train a new model, or it could be technically used for other purposes, such as fine-tuning the foundational model, as we are doing with language models. Or to do, I don't know, a conformal prediction and say to make a more robust prediction interval for your prediction. That might be more accurate. And here's basically what they try to sell you, not in a bad sense. Okay, this is the promise and the lure and the fascination by these models, which doesn't mean that they're going to replace the kind of model that we've all been using. And this is fairly important. We're not going to stop using training ARIMA models. I think that's this. If these pick up, if these models prove to be a thing, I don't think we're ever going to stop training ARIMA models or other ETS models, because they do like a lot of stuff and can bring you really far away. But they can give you a different tool that you can use that can make it easier to work with in situations where you have less data, or where you have different kind of tasks from your goals and from your requirements, such as providing robust prediction intervals, for example. So the lure about this, and I'll make this point again and then we can move on, is that maybe these models can help you be more clever about the data that you use and how you use it. And this is the real big thing, though. Is there enough data to train those models? Because for usage, for inference, we might have, but can we build those models reliably? Are we now at the same stage where we can get decent newer generation of foundational time series model, like every week or so? Like last week was Pixtral, yesterday we had Molmo in the domain series, in the vision and multimodality. So where are we at in terms of data? Because if there is one thing that like the latest developments in generative AI have shown us, that data is all that matters in the end. I mean, architectures are mostly standardized, and if you can do a lot of variation of attention layers, you can have group query attention, blah, blah, but in the end, it's just about data and how you can get better and better data, and how you can lead into better and better models. So the same will apply to time series, even if worse might be It may be even more important than that. So do we have enough data? And the quick answer is, sorry for the preamble, maybe not yet. We're getting there. We are starting the path to get there. Because insofar as open time series datasets, we don't have much. We didn't have much until this year. The folks at Monash University, for example, like the Professor Rob Hindman, if you know about him, he's really famous and has done an amazing job. And in his research group built the Monash time series forecast repository, which has, as some papers reported, like a bit less than 1 billion, even less than 1 billion observations. And so this year, the folks from Salesforce built Moirai, which is a time series foundational model, which has more than 27 billion observation across a huge number of time series datasets. This is the kind of scale that we have now. Is this enough? We're still figuring out. But we're not starting from a huge base, because even the time series Pi, which was introduced fairly recently with the Moment model, by a group, I don't remember the research group right now, but all of the links are there, so you can get the slides and click on it, and we'll be brought to the papers, etc., and repositories, official repositories. Well, the time series pile has 1.23 billion observations. So from a dataset standpoint, we do not have any common crawl. We don't have any real pile equivalent to that. Though curation will be another big concern, and we still don't know. The research that we found hasn't gone a lot in the direction of distilling those datasets to find out the true signal in all of those datasets. And also, which is a really big concern, there aren't any standardized datasets for benchmarking. So we do not have a GSMQ8, for example. Datasets that we run our new model against to figure out how they work. So the benchmarking is really sparse and diverse, which doesn't mean that it's not valid, but you should be extremely cautious when you try to evaluate those solely based on the author claims. So you need to build your own, you will need likely to maintain your own private datasets to maintain the data on. And this also is a really huge telltale signal about pay attention to contamination. Papers are extremely transparent about this, so if you go through, and many will publish the code, you will see the data that they use, but do not pick the claims lightly, because some papers might train on the same data that they might eventually rank the models on. You cannot just assume that the benchmark is good just by looking at the press release or the LinkedIn post that you see from your average LinkedIn influencer. So you need to be a bit more thorough and go through the papers, which are fairly easy to read, I would say, very well explained, and they did a really great job. So on the time series data, we're not really great point. And if you look at the papers, you will find that lots and lots of those papers use synthetic data. So basically, they do some kind of combination, and we go a bit through that to see how they do and what they behave. But the really interesting takeaway is that if you look at the Kronos paper, for example, they did a sort of an ablation study where they varied the percentage of synthetic data in the training process, and they found out that at least 5 to 10, maybe 10% or even more can really improve the diversity of the data so that the model can have better in-domain and even out-of-domain performance. And we're going to see that when Gabriele talks about the evaluation. So given all these huge premises that took 13 minutes, we can start talking about models and architectures. Here are just all the models that I could get my hands on that were reliable and open source this year. It's just 1 year, and we're going to talk about Kronos and TimesFM, one from AWS and another one from Google, just because we don't have enough time to talk about all of those. Moirai is another interesting one. We want to talk about those because they have two different architectures, which have really some interesting details that we would like to delve a bit into. And also, they explain a lot about the synthetic data generation procedure they use. TimesFM, for example, is a public repo, also Kronos, so you can also use it immediately, out of the box. TimesFM has released the code in September to do parameter efficient fine-tuning if you want to experiment with that. So they're really by far the most complete that we found. Even Moirai is really great, but time is what we have. And they describe really well all of the training steps, including ablation studies. So it's not to say they are the best ones, but we found that the most interesting for this kind of audience and for the first time that we give out this talk. And let's talk Kronos. And I really like this one. And because Kronos, it's not like a model, it's a framework that is used to train a family of models. And it's really clever in its ingenuity and its simplicity. Basically, the authors, what they did a really smart thing is say, hey, we have a really huge repository of existing architecture that work for language. We have a huge repository of training and code bases used to train those models. So let's just take a model such as T5 or GPT-2 and the architecture. We keep the architecture unchanged. We just retrain from scratch. Now we have a problem to turn the continuous time series dataset into a finite dictionary, but we do that through quantization. So you apply mean scaling, as you see here in the first step, in this part, and then we discretize the time series into bins. So basically, if you think about it, it's just say, okay, if you define beforehand a number of bin, they defined like a number of bin between like, if I think it's 4,000 bins. And so every continuous value that falls inside the bin, it gets discretized into this discrete dictionary. And then they train the T5 model from scratch. And this doesn't have to be by far the most efficient model to get out of here, because if you think about it, this thing about zero-shot models is all about efficiency in the forecasting process, is to getting from zero to production basically as soon as possible. This is my personal take, but they also stress about the efficiency about all of this, which is really clever if you think about it. And so this makes it really trivial to generate prediction intervals, because you know that like a model like this is basically a classification model that outputs the logits of all the possible tokens. So if you need to deliver a probabilistic forecast, you don't take the maximum of the logits, but you take something like that resembles the top K thing that we do when we try to sample from our large language models. And you don't even have to do that yourself, because this might be just a really thin layer on top of what we have with Hugging Face. So it's really easy to get something done. And it's not like a not fancy architecture. And so they devoted all of the time on the paper about training, the data they used to train the model and the data they used to evaluate it. And insofar as training comes, they use 55 datasets from the forecasting repository from Monash, M Competition, public Kaggle datasets. They took 13, which only were used for training, 15 which were used for further training and in-domain evaluation, and 27, so like a huge deal of the data that was there, was only used for out-of-domain evaluations. So the data that was never seen by the model upon training. And Gabriele is going to tell you anything about the training and the results and how this turned out. And then they delve up about two strategies they use to generate synthetic data up like to 10% or a bit more, even a bit more during the training process. And this basically boils down to convex combination of existing time series, with the first one, which is called TS mix-up. So basically you see here in the image, you have real original time series datasets, and you basically sample weights from a Dirichlet distribution, and you combine subsets of time series, even more than two, into generating a new time series dataset that uses different combinations. And then they use another series, which I haven't shown, but conceptually really analogous, like similar to understand, which is kernel synth. So basically they have a set, which I call a bank of kernels, a set of foundational patterns from time series models, for example, step function trends and stuff like that. And then they combine them through addition or multiplication to derive new time series. And they put all of those inside alongside the training data set, the run model.fit, using the same architecture about T5 models and semi-initialization, but they also found that if you initialize those without the same weights, you achieve the same results, and voila, you have the model. And the evaluation are thorough, but the one peculiar thing that they found out is that maybe the exponential trends in the dataset might have been a bit underestimated. So the model struggles a bit with exponential trends. And if you look about like linear trends, the model might fail to pick them up if it doesn't have an adequate enough context length, which is like a decent fact. I mean, it was really transparent about this. And if you look at it, this is the air passenger data set, but they also like they didn't do this all the time. So it's just like I picked like I'm cherry picking here, but this is the only minor detail that I found in the paper. The ablation studies or the hyperparameters are really thorough, and you might enjoy reading those. They're really accessible. But this is basically the only like negative outlook that I found. And that being said, I think we can move to the second thing. I can switch places.
Yeah, so we've seen Chronos, but just to give you an idea of where the research is heading and how little standardization there's to this moment, let's take a look at TimesFM, which is from Google Research. And basically what TimesFM research, what Google Research authors did was try a new architecture. So we've seen with Kronos that basically we are reusing existing LLM architectures, and now we are trying a new one, although not really different. So we can still recognize our our usual transformer architecture. We have this gray layer, which is basically just a standard out of the box transformer, causal self-attention, of course, layer. But the real innovation comes in the input layers. So we've seen with Kronos, we have a clever tokenization. So we just basically take the time series and we quantize it. While Google takes a different approach. They take patches. They say that basically the atomic element, the fundamental element is not the quantized time point, rather it is a patch. So we have, in this case, 32 time points constitutes a patch, as we can see here. And this patch becomes a token with a MLP plus residual connection layer. So we have tokenization and we also have positional encoding, but basically this is where the approach really differs. We're still equating time series to words, to language, but we're saying that the basic component is a patch, not a single data point. And after that, after having tokenized our patches, then our run-of-the-mill transformer architecture. And this is how it works, basically. So a bit of innovation, not so much. After that, we have an output of 128 time points, because it constitutes an output patch again. And also we have masking to improve efficiency in training, but this is really just a detail. About the data, the main interesting thing is which data they used. We have Google Trends and Wikipedia page views, which is a rather big data source, about 100 billion time points, which I find really interesting. And then we also have synthetic data, as we've seen with Kronos. Google researchers say for time series grammar, right? If you can provide a real-world series to your model, you can at least provide the grammar of the time series and hope that the model learns to reconstruct the real data from these patterns. So in a really similar way as they did in Kronos, we have generators of stochastic processes, seasonal patterns, strands, step function, and stuff like that. And then during training, we just mix those to provide the complete information to our models. How about hyperparameters? Like why they took the choice that they did take? Well, of course, we're seeing that increasing model complexity still pays off. Like bigger models work better. We haven't reached a plateau yet. There's still a lot of room for improvement. This is output patch size, so the size of the output patch that we use for prediction. And still, we can see that the longer patch size is, the better. This is, of course, a measure of error, so the lower the better. But they find that there's a satisfactory length for output patch size, although it could be argued that we can go forward with that. Input patch size, same. There's like a sweet spot at 32. So like they found this really good combination of parameters where you feed like 32 data points and you spit out 128 data points, and that's the sweet spot for them. This is, of course, depends on the data that they use. We cannot take too much. We cannot take this for granted. And they also did some data ablation, which is really interesting because they basically realized the actual usefulness of synthetic data. They tried, for example, this first data set, Monash, is full of data which has a frequency which is really underrepresented, 15 minutes frequency, which means that in the training data, we don't have as much of this data. And so the model actually performs slightly worse than in other cases. But synthetic data helps this. So we can see the green bar is lower. When we add synthetic data, we actually can recover a bit of precision by feeding the model these fundamental patterns, and so the model has to build their own 15 minutes data patterns from these fundamental ones, which I think is really interesting. So we can spend other hours talking about other architecture, but you want to know which one to use, okay? We can tell you that right away. Benchmarking is really different. As Luca said, there's no standard data collection. There's risk of benchmark pollution. So for example, here we have data from Times FM, which tells you that Times FM is the best model, but of course it is evaluated over the dataset that was used to train it. Also metrics, which metrics do we use? We know that forecasting can be point forecasting or probabilistic forecasting, so we have kind of double the evaluation. We also need, and Luca told us before, out-of-domain data, because if we want a zero-shot forecaster, we need to evaluate it on data out of what it has seen before. And also we have fine-tuning, which is another possibility. So lots of dimension, lots of possibilities. It is really different. So it is really difficult. So to wrap up, because I'm running out of time and of breath. Foundational models are on the rise. I haven't even drank my water to save time. So foundational models are on the rise, and we're gathering bigger and bigger collections of data. We also have synthetic data to help us, and there's a lot of improvement, as we've seen with hyperparameters, for example, where like if you increase model complexity, we can still get better and better. And also we have fine-tuning, which is really powerful. But we don't have public benchmark yet, so how can we choose right now what to do if to use these models? Well, we should do our own testing. Like if we want to take something into production, we should test ourselves with different architecture, from local standard ARIMA models to these amazing breakthrough foundational models. Let's test everything in between and decide on that. There's a really limited amount of public data yet, also because of the nature of the data. Like internet is full of text, it's not full of time series, unfortunately. And we are not even sure that the performance will scale. Like we've seen hyperparameters charts like getting better and better, but we're not sure how that will extrapolate outside of what we can test right now. So this is it. I think we're in time. Thank you very much.
So we just have 1 minute or two maximum. So if you have a quick question. Yeah.
Finally, you can drink.
Yes, hello. My question is, which model is the best for long-term forecasts? And have you found a combination of a model that's overcome the shortcomings that one model has with the other?
I'll take this one because it's drinking. So I think they wrote something out. So insofar as Times FM is concerned, they've only used like 128 output patches, so they didn't do any ablation run on the length. I mean, they found out the sweet spot, but they didn't go through beyond that very much. So for really, really long-term forecasts, even the Kronos paper, I believe, I should double check the content, so don't quote me on this one. They didn't do a really thorough evaluation, or I don't remember any thorough evaluation on the sequence length. So out of those that I saw, maybe Moirai has something, but I don't really remember whether they really were talking about long-term forecasts. Granted that if you aggregate the time series and provide, I don't know, monthly data points, you will generate monthly up to 128 data points for the monthly prediction with Times FM. So technically you can cheat out that by aggregating. The only thing is, if you input data, you will get data out, data of the same frequency. So you cannot put in data of 15 minutes and take out like 1 month. So you can cheat out with that, but you should run your own benchmarks, basically.
If I can just add one thing, like the Times FM paper says that basically they found out that if you have a long horizon, it's better to predict it in one shot than to do auto-regressive decoding like I show in the Times FM architecture. But foundational models need to have like a single output length, and so you cannot know in advance the horizon of your application, and so there's like a trade-off. So that's why I didn't tell it because of the time, but that's why I chose 128 for output, which is significantly larger than the input, because they wanted to do a longer output, but they couldn't know in advance like the usage that this model will have, so there was like a trade-off. But they realized what basically the answer to what you're asking, like choose the model that predicts it the most in one shot. At least that's what they say, because with auto-regressive, the errors like build up and can potentially explode. So, but we didn't test it, to be honest.